Several years ago, I was sitting in my office and the phone rang. I answered the phone and he said, "Hi, my name's Frank. I'd like to come talk to you about counterfeit Cisco routers." And I said, "I don't really know anything about that." And he said, "Well, I read one of your papers. I think you can help us." I said, "Okay, do you want to come sometime next week?" He said, "I want to come tomorrow." I'm Professor Mark Hinders, Applied Science Department at William & Mary. The problem that Frank came and told me about is a real problem. The issue is that the supply chain for microelectronics is now global. And if you have a whole bunch of, say, memory chips from a Cisco router, there's really no way to tell where the individual components are manufactured. And there are people who are quite concerned about this. They're concerned that nefarious types might insert into the supply chain counterfeit components that either wouldn't be reliable or would be merely masquerading as the real component but have some extra capabilities in it that would cause snooping or some other sort of thing. And so what they really wanted was methods to work on the loading dock in order to open the top on, say, a Cisco router and check whether certain components were what they said they were going to be. The particular problem that we settled on to study over not quite a year, about 9 months, was developing a method to identify delamination flaws in memory chips that are often in Cisco routers. So recycling is good. But recycling computer chips can be an issue. And there was this weird time where the solder that's used was made more environmentally friendly. So it used to have lead in it, and the new ones don't have lead in it. And the new, more environmentally friendly solders melt at a higher temperature. And so if people were recycling chips by taking them out of some old component, putting them in a new component, this difference in the temperature could be a problem. Also, if you don't carefully get all the moisture out of a chip before you desolder it from the old board, you can get, the heat causes the moisture to go to steam, and you can get popcorn delaminations in the chip. So this was the demo problem that we worked on. Could we develop a technique to find delaminations in computer chips, memory chips, in a way that could be done in a practical situation, for example, on the benchtop in a workshop rather than a specialized inspection laboratory, so that one could check in certain situations whether a chip was flawed or not flawed. And we had developed techniques some years before that are used in acoustic microscopy to find flaws in microelectronics packaging, but done at the production stage before they're in devices. And that's the paper that Frank had seen. And so our challenge was to adapt fairly standard high-frequency ultrasound inspection techniques to practical applications. Not difficult in the sense that if you have a solid material with some delaminations inside of it, ultrasound will reflect from the delaminations, and the time delay of the reflections will tell you the depth of that delamination. And if you scan across an area, you can map out the areal extent of the delaminations. This is all pretty well known. If the thing you're inspecting can be immersed into a little bit of coupling fluid, typically water, and then the scan is done under computer control. The challenge is to do this in a practical situation. So we first got ourselves a bunch of chips, and then we built a system to introduce moisture into them. Here you'll see an oven that we had that we set up to saturate the chips with moisture. Okay. And then we used a solder reflow system to introduce heat into them once they've got the moisture in order to make the popcorn delaminations. And at very high frequencies, say 100 megahertz, it's relatively straightforward to do a pulse echo measurement. You can see the A line there, the reflections, but then also a couple of wavelet fingerprints, and you see the difference between the flawed and the unflawed thing. So that gives us in this abstract wavelet fingerprint representation a simple feature to look for to tell the difference between delamination and no delamination. All right. Now the challenge becomes, how do you make this work in a practical situation? And so I have a very talented engineer, Jonathan Stevens, who prototypes for us. And Jonathan designed a system that holds the transducer and a very fragile delay line to give coupling over a small spot of the surface of the thing, and then you can scan over the region by hand, take various point measurements, and then record the A lines, convert those to the fingerprints to tell whether there's a flaw or a not flaw at each of the locations. The challenging part about that is the thing is very fragile, and at high frequencies, the spatial precision and getting the coupling just right by having the transducer and the delay line oriented properly turn out to be fairly tricky. And so that worked quite well, and we collected a bunch of data on flawed and unflawed samples, and what we found is looking for that particular feature in the wavelet fingerprint. It's either there or it's not there, indicating the presence of the delamination, and that allowed us to very quickly and automatically with a manual inspection map out the area of a chip and see if it's flawed or not flawed. We use just a little bit of water on the surface for coupling, but a small enough amount of water that this could be done in a router with the chips installed. You wouldn't have to remove the chips, and so it's a practical measurement technique. Okay? And so we did this start to finish over about 9 months, I think, and then delivered the prototype and hardware and software and the fixtures to the sponsor, demonstrated in their conference room, and then they presumably took it into their back room where they used it for inspections. And throughout the project, one of the things that was interesting for me is it struck me as odd how sort of paranoid they were about this issue, because there were lots of other people who were working on other aspects of the problem, trying to detect when there's some counterfeit nature to chips in, for example, a router. And I found that all a little bit strange. And then a few years after we finished, the WikiLeaks dump came out, and I saw this slide among them where it's talking about a secret program top secret program to intercept things, say routers, open up the box, take them out, swap out some components, seal it back up again, presumably Photoshop the tracking numbers and whatnot, and send it on its way so that when the package shows up at the new destination, the recipients don't know that it was intercepted along the way and modified somehow. Okay. So, interesting project, relatively straightforward from the scientific aspect, but the practical engineering aspects of making it work in the loading dock sort of situation was really quite interesting. I'm Professor Mark Inders, Applied Science Department, William & Mary, as.wm.edu.